This is Unit 2, Video 3. In this video we'll talk about the states, also called the phases of matter. And this is the solid, liquid, and gas phases. So let's talk about gases. Gases, by definition, have no definite volume and no definite shape. What this means is that if you take a bottle of a gas, the gases spread all throughout that bottle. Now, if you were to open this up and allow the gases to escape, the gases will actually go all over the place and they will not keep this bottle shape. They'll actually spread throughout the room and will have no definite shape. And they also won't have a definite volume. So that's because they can easily spread out. That's because the gas molecules don't have any attractions for each other. And as a general rule, the particles are far apart and have very rapid motion. So these particles are actually moving at a really, really high speed, faster than the speed of sound, actually, at room temperature. And that's why they're able to spread out throughout the whole room. Eventually, all these particles will be spread out everywhere. You will not be able to contain them because they're a gas, and they will not have any sort of shape or even any sort of volume. And that's for gases. Now, liquids, on the other hand, have a definite volume, but no definite shape. So what this means is that if you have a liquid in a bottle, like here, you can actually measure the volume of this bottle. Maybe it's 0.5 liters, but there's no shape. In fact, if you tip the bottom or tip the bottle on the side, the shape of the liquid changes. If the liquid is in a bottle that's standing up, the liquid has, kind of a rectangular shape, whereas if the bottle's lying down, it's just changed its shape, and that's the idea. Now it has more of a cylindrical shape, maybe you can say. And so the liquid particles can move around, and that's why they're able to change their shape. So they have an indefinite means not definite shape, but they have a definite volume. Now here it says the particles are touching. If the particles are touching, that means the particles actually have an attraction for each other, and that's correct. These particles are actually attracted to each other, that's why they're touching. And they can slide past each other. So the attraction, you can say, is not very strong because the particles can kind of move past each other, and that's why a liquid flows. That's why you can actually pour a liquid out. And sometimes as it flows, the particles end up in 2 or 3 little puddles, and that's because the particles do have an attraction for each other, but not a very strong attraction as compared to a solid, as we'll see. And that is the third type of matter, or third phase of matter, and that's a solid. Solids have definite volumes and they have definite shapes. So by definite volume, we mean if you have a big cubic piece of solid, it'll keep that shape no matter what container it's in. And the particles here are closely packed together, which means they are the closest they can be compared to a liquid or a solid, but they also vibrate. So the particles are actually not standing still in terms of they have energy. In fact, here is 2 pictures. Here's a picture of particles at a cold temperature and at a hot temperature. There must be a difference between the particles. Now, the hot temperature, it's still a solid. So, for example, think of a piece of metal that's hot. It's still a solid. It hasn't changed its shape. It's still in this cubical shape. But the particles have to be doing something different because there's 2 different temperatures. Well, what they do is they vibrate. So you can see the vibrations are bigger here when it's hot. The vibrations are slower here when they're cold. But they do have movement, and that movement is a vibrational type of movement. So those are solids. Now, the question here asks which are more dense, solids, liquids, or gases? And because in a solid the particles are closest together, this gives you the highest density. Now, the least dense must be the gas particles because they're least packed together. Usually for a solid, say if you have a density of 2.5 grams per milliliter, for a liquid, that will be slightly lower. So maybe you have 2.3 grams per milliliter. Usually, there will not be a big difference between a solid and a liquid. But for a gas, the difference is about 1,000 times less. So here you'll actually be 0.003 grams per milliliter. And that's why usually they express densities of gases not in grams per milliliter, but in grams per liter. In this case, it would be 3 grams per liter. About 1,000 times less dense. So gases definitely are the least dense of the bunch. And usually solids are the most dense, and liquids are somewhere in between, but much, much closer to the solid densities. Now this is true of most substances, but not all substances. In some substances, these two are actually flipped, or the densities of these two are actually flipped. Now let's show you that. So here's a very famous exception, water. The most common substance that we deal with has its solid phase less dense than its liquid phase. Now the reason why this happens, here is a picture of molecules of water actually combining together and freezing, going into a solid, and the molecules actually line up to where they have openings between the molecules in the solid phase. And these openings allow them to expand. And because it expands, the density is less. And this is why ice floats. Very famous effect. And it's actually a rare effect. Most solids will sink in their own liquid, but ice actually floats. Now, ice has a density of about 0.9 versus water, which means it's less dense than water, so it floats. If you take a look at a huge iceberg, for example, about 10% of the iceberg is above the water, and about 90% of it is below the water. So when you see ice on top, then there's 9 times as much stuff down below. And that's because the density of ice is about 9/10 gram per milliliter. There are other substances like this, but again, they are rare. There are a few elements that have this exception as well. The solid is more dense than the liquid. And there is a fourth state of matter that we usually discuss, and this fourth state of matter is called plasma. Now, plasma is a really high temperature physical state in which atoms lose their electrons. We'll talk about electrons in the next chapter, but electrons are the particles that are circling around the atom. So these little tiny particles, and these particles can be ripped off. When that happens, you actually create plasma. And usually the plasma glows. So this, for example, is why the sun glows, why stars glow. And here we have a plasma state, and you see this very, very bright glow. And that's because we are reaching a very, very high temperature. Lightning is another example of it. So what happens is you can get a substance to go from a gas to, you get a substance to go from a solid to a liquid by adding some heat, adding energy, from a liquid to a gas by adding more energy. And if you keep going, you can actually get a gas to become plasma. And a lot of energy is required for this to happen. So the sun, for example, has a lot of energy. There's a lot of energy in lightning, and that's why plasma occurs. Alright, so we should say that the phase a piece of matter is in depends on how much energy it has. And in a way, you can say how hot it is. So obviously the solids are the coolest, the liquids next, and the gases have the most energy. And we can talk about energy changes along with their phase changes. So here are the names of the different phase changes. This is really important to be able to know. The names of these phase changes are melting, is what we call going from a solid to a liquid. Freezing is the opposite way, liquid back to a solid. These two, the students usually know coming in. This is kind of common knowledge. The next two are vaporization and condensation. They're also opposites. Vaporization is going from a liquid to a gas. Now there is another phase change called evaporation. Evaporation is close to vaporization, but evaporation happens at room temperature. And if you think about this, if you have a glass of water just kind of sitting there, over time, the glass of water will evaporate, but you don't have to put any heat into it. That's called evaporation. If you have to put heat into it and it's actually boiling, that is called vaporization. The opposite is called condensation. And then the last two, sublimation and deposition, are phase changes in which the liquid is bypassed. So we actually don't go into the liquid, we go directly from a solid to a gas, or a gas to a solid. For deposition, think of this word deposit. As it becomes a solid, you deposit something. And these two are usually new, so make sure you know sublimation and deposition as definitions. So what we'll do is we'll talk about the energies associated with these two. So anytime you go from a solid to a liquid to a gas, this will be called an endothermic process. And this is the energy that is being placed into it. Endo actually means, this word endo means into, and thermic means energy. Thermo is energy. So you have to put energy into the water to go from a solid to a liquid to a gas. Now this makes sense. Say if you're trying to boil water out, you have to put energy into it. You have to put a Bunsen burner to it, for example, to really get the energy so it becomes a gas. And that's why it's called an endothermic process. Heat is absorbed by the system being the chemical there. And the reason why this happens is because bonds between the molecules must be broken. And those bonds to be broken, you have to put energy into them to break them. So anytime you go from a solid to a liquid to a gas, it's endothermic. So obviously the opposite would be exothermic. If you go from a gas to a liquid to a solid, this is an exothermic process. Exo means out, and against thermic refers to heat. So heat comes out. Heat is released by the molecules as this happens. And this is because bonds are being formed and extra energy is released. So because it's the opposite of what happened before, the energy change is then opposite as well. So hopefully this makes sense. We're going to talk about the heating curve in video 5.